Many of the chemicals you encounter in your daily life are ionic compounds. These include table salt, or sodium chloride, which is used to preserve and flavor food, the fertilizer ammonium nitrate, which fueled the development of high-volume, intensive agricultural practices during the 20th century, and is produced in massive quantities, the compound sodium fluoride, which is added in small amounts to toothpaste as a means to enhance the strength of teeth, but also has been used in larger doses as an insecticide or rodenticide. Note that toxicity is a function of dose. Even water can be toxic when ingested in too large of a quantity. In this presentation, I will introduce ionic compounds. I will talk about anions, cations, and the structure of ionic compounds, which naturally leads into understanding some of their properties. I will then review how dot structures and the octet rule can be used to predict the charge of common ions of the elements, and introduce polyatomic ions. The formula units of ionic compounds and how they are determined by charge neutrality will then be discussed. Finally, I will describe the naming of ionic compounds. Ionic compounds are made up of ions. An ion is an atom or compound that has an unequal number of protons and electrons. This imbalance leads to a net charge, either positive or negative. A positively charged ion is called a cation. A cation has more protons than electrons. For instance, consider the lithium atom, which has 3 protons in its nucleus, balanced by 3 electrons in orbitals. If one electron is removed from a lithium atom, a lithium cation is formed. A superscript is used to indicate how many more protons there are than electrons, in this case 1, and this number is followed by a plus symbol. In other words, the superscript is the charge in the ion in units of the elementary charge. It is conventional to omit the 1 when dealing with a singly charged ion. A negatively charged ion is called an anion. An anion has more electrons than protons. For instance, consider the fluorine atom, which has 9 protons in its nucleus, balanced by 9 electrons in orbitals. If 1 electron is added to the fluorine atom, a fluorine anion is formed. A superscript is used to indicate how many more electrons there are than protons, in this case 1, and this number is followed by a minus symbol. In other words, the superscript is the charge in the ion in units of the elementary charge. Again, it is conventional to omit the 1 when dealing with singly charged ions. Positively and negatively charged particles are strongly attracted to one another. The attraction between anions and cations leads to the formation of an ionic bond that holds ionic compounds together. Most ionic compounds are solids at room temperature. In these solids, a large number of cations and anions are held together by ionic bonds to form a very large network or crystal. The structure shown here only represents a piece of an ionic solid. In reality, the structure would extend in all directions. This extended structure is unlike the molecules making up covalent compounds, where a relatively small number of atoms are held together by covalent bonds. This difference is also important in how we think about the chemical formula of ionic versus covalent compounds. For a covalent compound like ammonia, the chemical formula NH3 tells us that there is a molecule containing 1 nitrogen and 3 hydrogen atoms. What does the chemical formula for sodium chloride, NaCl, tell us? Instead of being based on discrete molecules, the structure of an ionic solid is an extended one containing many sodium cations and anions of chlorine known as chloride ions. As with covalent compounds, the chemical formula tells the ratio of sodium to chloride ions in the structure, but it does not describe a molecule. Instead, it describes a formula unit. A formula unit is the smallest representative unit of the compound. In this case, 1 atom of sodium and 1 atom of chlorine. Some characteristic properties of ionic compounds. They can be formed from the reaction of a metal with a nonmetal, among other ways. This is in contrast to covalent compounds, which typically contain only nonmetals. Remember that the metals are the elements on the left side of the periodic table, and the nonmetals are on the right. The strong interactions between ions result in a high melting point. As was mentioned earlier, most are solids at room temperature, consisting of an extended network of anions and cations held together by ionic bonds. Ionic compounds are hard but brittle. They are brittle because a small dislocation of the structure can place like-signed ions, plus with plus and minus with minus, next to each other. Like-sign ions repel each other, contributing to the fracture of the crystal. Many ionic compounds dissolve in water to form electrically conductive solutions. Water interacts strongly with ions, causing the structure of an ionic solid to break up, giving free anions and cations. As these ions are charged, the resulting solution can conduct electricity. The picture shown is a cartoon of water, H2O, hydrogen in blue, and oxygen in red, in which an ionic solid is dissolved to yield free anions in yellow and free cations in green. Elements form ions of certain common charges, as shown in the partial periodic table below. The blank spots are elements that do not commonly form ions. Some trends are apparent. The metals form cations. The nonmetals that form ions form anions. For main group elements, elements of the same group form ions of the same charge. For the main group elements, these observations can be understood in terms of the octet rule, or the special stability of a filled valence shell. As seen by the dot structure, the noble gases have filled valence shells. This is 2 valence electrons for helium and 8 for the rest. To form an ion, they would need to gain or lose an electron. This would break up their octet, and so the noble gases do not form ions. Consider the reaction of a magnesium atom with a sulfur atom. The electron configuration of magnesium is 1s2, 2s2, 2p6, 3s2. A shorthand for this comes from writing the first part of the electron configuration as that for the neon atom, or neon, 3s2. The electron configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4, or neon, 3s2, 3p4. Note that if 2 electrons are transferred from the magnesium atom to the sulfur atom, this leaves a 2+ charge on the magnesium and a 2- charge on the sulfur. The resulting electron configurations are neon and neon 3s2, 3p6. Note that both ions now have noble gas configuration, satisfying the octet rule. The loss of 2 electrons from magnesium results in a filled n equals 2 shell, an electron configuration matching the noble gas neon. The addition of 2 electrons to sulfur results in a filled n equals 3 shell, and an electron configuration matching the noble gas argon. This explains why magnesium and other elements of its group with the same number of valence electrons form 2+ ions. It also explains why sulfur and other elements of its group with the same number of valence electrons form 2- ions. Drawing generic dot structures of the main groups, one can see that adding 1 electron to group 7a elements, the halogens, results in a filled octet, so elements of this group form -1 ions. As we have already seen, group 6a elements form ions of -2 charge because adding 2 electrons form a filled octet. Elements of group 1a, the alkali metals, lose 1 electron to form ions of +1 charge. It may appear that there are no valence electrons from the dot structure, but recall that there is an underlying filled shell. Elements of group 2a lose 2 electrons to form a 2+ charge, and aluminum forms an ion of 3+ charge. The transition metals do not follow the simple octet rule, so the common charges of their ions are not as simply predicted. Note also that some of the transition metals, such as iron, have more than one common charge. When ions come together to form ionic compounds, they must preserve charge neutrality. That is to say that the number of positive charges must balance the number of negative charges. The relative number of anions and cations in an ionic compound is expressed by its chemical formula, and our understanding of the common charges of ions can be used to predict the chemical formula of ionic compounds. For instance, sodium chloride is made up from sodium and chloride ions, with charges of +1 and -1. For the positive and negative charges to balance, there must be an equal number of sodium cations and chloride anions, because they have the same magnitude of charge. The ratio of the two must be 1 to 1. The chemical formula is Na1Cl1, or just NaCl. One positive charge plus one negative charge gives a net charge of 0. A pictorial representation would be to view the balance of positive and negative charges in terms of the pairing of ball and socket joints. A positive sodium atom with its +1 charge can be viewed as having one ball joint, and a chloride anion as having one socket. These pair together in a 1-to-1 ratio. As another example, consider the ionic compound magnesium chloride, formed from magnesium and chlorine. The common ion of magnesium has a charge of +2, and the common ion of chlorine, the chloride ion, has a charge of -1. For the negative and positive charges to balance, two chloride ions must pair with each magnesium ion, so the chemical formula for this compound is MgCl2. Adding the charge on one 2+ ion with that of two -1 ions yields a net charge of 0. With the ball and socket analogy, the positive 2 charge on the magnesium would be represented by two ball joints. Each chloride has only one socket. To balance, these pair together with two chlorides for each magnesium. How about the chemical formula for rust, or iron oxide, which is made up of an iron cation of charge +3 and oxygen anions, known as oxide ions, of charge -2. Considering the ball and socket representation, with one each iron and oxide ion, there is an excess of positive charge. Adding another oxide anion now results in an excess of negative charge. Adding another iron cation now results in an excess of positive charge. Finally, adding a third oxygen results in charge neutrality. 3 oxide ions are needed to balance 2 iron ions, and the chemical formula is Fe2O3. 2 ions of charge 3+ added to 3 ions of charge 2- give a net charge of 0. The ions we have discussed up to now are all single atoms. There are many ions that consist of atoms of more than one element covalently bound together. These are called polyatomic ions. The structures of 4 common polyatomic ions are shown. They are the ammonium cation, NH4+, the hydronium cation, H3O+, the carbonate anion, CO3 2-, and the sulfate anion, SO4 2-. Parentheses are very important in writing the chemical formula of ionic compounds containing polyatomic ions. For instance, consider the chemical formula for ammonium carbonate, which is the compound formed between the ammonium ion and the carbonate ion. As the carbonate ion has a -2 charge, 2 ammonium ions are needed for charge neutrality, and the chemical formula is written as NH4 in parentheses 2 CO3. Normally, a subscript on a chemical symbol indicates the number of atoms of that element. The parentheses tell us to multiply the 2 by the subscripts on all of the atoms within the parentheses. Without the parentheses, the chemical formula would read NH42CO3 and would be interpreted as there being 42 hydrogen atoms instead of only the 8 from 2 ammonium ions. Becoming familiar with common polyatomic ions such as these can help you better recognize ionic compounds based on them. Throughout this presentation, we have seen the chemical formulas of a variety of ionic compounds. There are some rules in writing them properly. First, the cation is written first, followed by the anion. NaCl, not ClNa. The smallest charge-neutral unit is written NaCl, not Na2Cl2. The charges are generally not shown. NaCl, not Na plus Cl minus. Parentheses are used to avoid confusion with polyatomic ions. Parentheses NH4 subscript 2 CO3, not NH42 CO3. You can usually identify a chemical formula as corresponding to an ionic compound by looking for a metal with a nonmetal or looking for one of the common polyatomic ions. There are also conventions in naming ions and ionic compounds. I start by discussing the naming of ions. Cations of the main group elements are simply named by adding the word ion. For instance, the ion of sodium is called the sodium ion, and that of aluminum, the aluminum ion. Transition metal cations can have more than one common charge, so the charge needs to be indicated. An older method of doing so used different suffixes for different charges, and is a method still used today. A newer systematic method uses a parenthetical Roman numeral to indicate the charge. For instance, the 2+ cation of chromium is named using the older method, chromous ion. Using the systematic method, chromium parentheses Roman numeral 2 ion. The 3+ cation is named the chromic ion. Or with the newer systematic method, chromium parentheses Roman numeral 3 ion. Note that the ion charge corresponding to the us and ik suffixes depends on the element, but the ik suffix always has a higher charge than the us suffix. Anions of the elements are named by replacing the ending with "ide" and adding the word ion. For instance, the anion of bromine is the bromide ion. The anion of oxygen is the oxide ion. Polyatomic ions have varied names that can be found in many tables. It is useful to note that some closely related polyatomic anions are named in a somewhat systematic way. For instance, NO3- is nitrate, and NO2- is nitrite. SO4-2- is sulfate, and SO3-2- is sulfite. Note that in this case, the ate and ite indicate a progression in the number of oxygen atoms, but that the specific number corresponding to each depends on the ion. Once you understand how to name ions, naming ionic compounds is simple. Just put the cation name first and then the anion name and drop the word ion. Remember, for transition metal cations, the charge needs to be specified. Here are some examples. MgCl2, magnesium chloride. LiF, lithium fluoride. K2CO3, potassium carbonate. FeCl2, iron 2 chloride, or ferrous chloride. FeCl3, iron 3 chloride, or ferric chloride. Note that in the older method for naming the iron salts, the Latin name for iron, ferrum, was used, which is also the origin of the Fe symbol. I will summarize this presentation by working a problem that covers some of its main points. What is the chemical formula of calcium nitrate? From the name, we know that there is a calcium ion and a nitrate ion. From a table of common polyatomic ions, we can find that nitrate is NO3-. The dot structure of calcium, recognizing that it is in group 2 of the periodic table, shows 2 valence electrons. By losing both of these, calcium can obtain a full octet, in this case the underlying shell, so the charge we expect for calcium is 2+. For charge neutrality, we need two nitrate ions, each of -1 charge, to balance the +2 charge on the calcium. Taking care to use parentheses with the polyatomic ion, the chemical formula is Ca parentheses NO3 2.